We're going to start with that, actually. And that is the case of equilibrium radiation. Okay? Now, such equilibrium radiation, in that case, we can use what is known as Kirchhoff's law, which actually states that the emission has to be balanced by the absorption coefficient times the specific intensity. Okay? That's Kirchhoff's law. Now you just plug this in here, and you see again that in such a situation, again, the I nu ds equals to 0, or I nu is constant. So in both limits, so to say, we get that the specific intensity is constant. Now, in this case, this is equilibrium radiation, and then the radiation field, specific intensity, is described by a very famous spectral shape function. The spectral shape that the specific intensity in that case has is given by 2h nu cubed c squared 1 over e to the minus h nu divided by kt minus I, which we then define as b nu, which is only a function of t. This is the Planck function, or Planck's law of radiation. As you can see, it is a very strong function of frequency. Yeah? It depends on temperature, not on density, on the material density, right? And ideally, in order for this to be fulfilled, the temperature actually has to be equal everywhere. Sometimes when we deal with radiative transfer, we will come to this later during the course, we can assume that this holds locally. For example, in plane parallel layers in an atmosphere around a star or in an accretion disk or something like that. Then this might hold locally, but not globally. Okay? And we will come to such local thermodynamic equilibrium situations later on. We will also look at, in the transition between chapter 4 and 5, at the origin of Planck's law of derivation, actually even repeating his original derivation of it, and see how it actually arose, which has a quite interesting history to it, because as you may know, this is where he first came up with it as basically a mathematical trick, a way to match what he found empirically, and then he came up with his quantum oscillator hypothesis in order to explain that, which essentially was the dawn of quantum mechanics, right? But for that, we need a little bit more knowledge. So we'll do that later during the course. For now, we will take Planck's radiation law for given, and we know it, and we will discuss and analyze its properties. Okay? So, now, first thing you can notice is the spectral shape. So if we, for example, now just do a very schematic plot where we plot something like the logarithm of a frequency, and then we have B nu for a given temperature here, there, at the low frequency limit, we will essentially have a power law behavior, and then we will have a peak and an exponential cutoff. So in this regime, we have a power law, we have some sort of peak value, and then we have an exponential cutoff. Okay. So let's see if we can understand this. Well, the power law dependence, we can use this, okay? And then we can make the assumption that, okay, low frequencies, h nu divided by kt, if that is much, much smaller than 1. So, and this is actually very important, where you reach this regime depends highly on the temperature. So if we analyze the cosmic background radiation today, which is very cool, on the order of 3 Kelvin, then we have to go to much, much lower frequencies or higher wavelengths in order to apply this limit than if we analyze the spectra from a hot star, which is perhaps 40,000 Kelvin on the surface. The important thing for this power law regime to hold is this, okay? Now, in this regime, we can apply a Taylor expansion, and if it's one Taylor expansion that you need to know in this course, it's this, that e to the x is approximately 1 plus x if 0 is smaller than x, and it's much, much smaller than 1. Okay? This will come back both here and then in the radiative transfer equation, etc. So that's a Taylor expansion. So we apply this there, because that's essentially what we have there, right? So then we can say that B nu in the so-called Rayleigh-Jeans limit for given t, that's 2h nu cubed divided by c squared, 1 over, and then I use this, so then it's 1 plus h nu divided by k2 minus 1. So this is interesting. We see a number of interesting features here. We get 2k minus c squared. Note how h is canceling. Then we get nu squared t. So in this Rayleigh-Jeans regime, we have one that for a given temperature, B nu is proportional to nu squared. We also have that it is directly proportional to the temperature, yeah? And we have gotten rid of Planck's constant, which is h, as we know. And this is indeed the classical limit. And we will see either at the end of today or next week how it also leads to what we call the ultraviolet catastrophe and what that actually was. Okay? You see the power law dependence there, right? Now, in the opposite regime, you have h nu divided by kt much, much smaller than 1. Did I really? Yeah, I sometimes. Now, in this, that is called then the Wien limit, okay? And then you can see that you're going to be proportional then to mu cubed e to the minus h nu kt. And as you know, if you're up against an exponential, you're always going to lose, which is indeed why you get this drastic exponential cutoff. The power law doesn't stand a chance. Yeah, that's a basic thing from calculus. Did I do something? Yes. Thank you. I was pointed out from the audience that both here I had h nu over kt much, much smaller than 1, and then I repeated it here. Hopefully I said it wrong. It should, of course, be much, much greater than 1 if I said it wrong as well. My apologies. Because if it's much, much greater than 1, you can see that you can neglect the minus 1 there, and that's the whole purpose. And that's how you can write it like this, okay? And that's how the exponential eventually will win out. The higher and higher frequency we go to, and we will get the exponential cutoff. Yeah? And that's indeed what was required in order to avoid the ultraviolet catastrophe, by the way. The third thing we said was, okay, can we do something useful with the peak? Well, actually, in astronomy, the peak turns out to be very, very useful. So we're going to look at that a little bit. But it's mostly intuitive and for further calculations also to do that in wavelength space rather than in frequency space. So then we have to take a little bit of a detour there to say that, and this is important, remember that when we introduce this specific intensity, you have to always think about that technically it's only defined in a small waveband interval, okay? Such that the preserved quantity is really b nu t, the nu is b lambda t, the lambda. That was the same for the specific intensity. So in order to get the wavelength version of the Planck function from the frequency-dependent version, we can't just plug in the wavelength there and then just have it. We have to also take into account the difference in the nu, right? So technically, one should always write that the real quantity that one analyzes is this one, right? So in this case, you can see that b lambda of t is just b nu of t, and then it's just the nu, the lambda, where of course we know that c equals to nu lambda. Now, your first little homework will of course then be to verify the version that you find in the book for b lambda of t. The second one is to, okay, we want the peak. How do we take the peak? Well, we just set the derivative for a given temperature, it's a function of lambda now, to 0. And then we solve it. Okay? Now, the interesting thing from an astronomical standpoint is here that when you do this, and that is the also an exercise to solve this integral and verify that indeed what you find is that the peak wavelength, lambda max, times the temperature of the blackbody radiator is always a constant. Okay? Lambda max now being the wavelength at which this is maximum, that is where the derivative is 0. Now, silly enough, I am not sure that I brought with me the constant, so I'm going to ask one of you to look it up in the lecture notes in some convenient units here. Can somebody do that? Or me now? Normally we have it in some inverse Ångström and Kelvin. Sorry? 2897.8. And what are the units then? Micrometer Kelvin, or was it millimeter? No. Micrometer Kelvin. Okay, nice. So there we can see here, right? So let's now assume that we observe something, say a stellar spectra. And that stellar spectra is not exactly a black body, as we know, but it's roughly a black body in wavelength space, so perhaps it's something like this. And then we observe that this peak wavelength here in that stellar spectra is, okay, it's at 500 nanometers, right? Now, what temperature is that? Okay, so then we have to see that the temperature then is 2897.8 times micrometer Kelvin. So we have to do this to micrometer. What is that? 0.5 micrometer, right? 0.5 micrometer. So this is going to be on the order of 5,700 Kelvin. Well, this is 900, so 5,800 Kelvin. Okay? Can we tell an object that might have a surface temperature roughly 5,800 Kelvin? The sun. And where's the peak wavelength of the sun, the emitted spectrum? Green, which is around 500 nanometers. This is an approximate, but you can tell that immediately by just looking at the spectra from any object, and in the lecture notes, in the course book, we have a few stars. You can just get the first guess of its temperature by just applying this. So for example, if a star is much hotter than the sun on surface, say 4 times hotter, yeah, then the peak wavelength will be roughly at 4 times lower wavelengths. So instead of at 500 nanometers, yeah, it's going to be at around 100 and 150 nanometers. Now, why is this important? Well, then we have actually gone to a different waveband. Then we're in the ultraviolet. And the ultraviolet, for example, we can't observe from here on Earth. This we have discussed, because it gets absorbed. So then we needed to shut up these telescopes into orbits above the Earth's atmosphere in order to observe various astrophysical objects in the ultraviolet. Okay? That was the James Webb telescope. Okay? Similarly, if you have a cooler object, yeah, then the peak wavelengths will be further to the higher wavelengths. So for example, if you now are interested in something like planets around other stars, so-called exoplanets, yeah, then you might be interested in wavelengths that are much, much higher, because the temperatures might be much lower. So perhaps you want to go to the infrared and observe those. That's where, for example, the James Webb telescope, the new one, is tuned to be very efficient. You can even apply this to galaxies. For example, you can look at the spectra from a whole galaxy, which then contains of billions and billions of stars, and then you can see, well, you know, this galaxy spectra from an elliptical galaxies has its peak in the wavelength very much to the red. Well, what does this mean? Well, no, to the red. Well, to the against the infrared. Yeah. Well, it means that the objects that are emitting, that is dominating this source, they have cooler temperatures. And typically, such elliptical galaxies are also called red and dead galaxies. They have no active star formation, so the young, very massive stars that shine a lot in the blue They have died out long since, and what is left are these red dwarf stars, such as our sun, and even more so, even lower mass, cooler stars. And then you see this directly reflected in the spectra from the whole galaxy, because the peak wavelengths are shifted to the red. And then you compare this to like a spiral galaxy with a lot of active star formation, or even a so-called starburst galaxy. There, the peak wavelengths, they will be shifted much, much to the blue. And that's because there are so much active star formation going on, such that there is a lot of these young, very massive, hot stars which are shining and dominating then the total light. So you will get much, much the light. And there's also some such galaxy spectra for you in the course book that you can notify. But realize that only by looking at this, we can already get a feeling for now the temperature of various astrophysical objects that come to us. And then and I will just leave you with that, what we will do next. Next week, we will finalize by looking at also the integrated properties of the Planck curve. Because what you should have already realized is that, okay, in the Planck curve, there is no density dependence, right? But there's also no angle dependence. So if we now plug in this, for example, in our energy density, right? Our energy density, remember, is defined as this, and then nu, 0 to infinity, and then we have I nu, right? So now we replace that with B nu of T divided by C, and then the nu, the omega. But there is already no angle dependence in the Planck function. The Planck function is, as it should be, because it's equilibrium radiation, isotropic. And this is where this comes back. So this we can already take out. It's going to bring 4 pi, and we just have to frequency integrate the Planck function. And then we will see what comes out. And indeed, when you do this now, for the full, you will get an expression. However, when you do this now in the classical Rayleigh-Jeans Blackbody, yeah, and you integrate this now, so it's 4 pi, and then nu 0 to infinity, and then B nu Rayleigh-Jeans of T divided by C, the nu, you will see that this indeed goes to infinity. And we will verify this, of course, and you can already do that if you wish, because you can just look at the expression and realize this, and this indeed was then what was called the ultraviolet catastrophe of classical physics. So already there, people knew very much that something is wrong here, because we predict that the radiation energy density from any given black body, whether it be me or a star, I'm a black body roughly emitting around 300 Kelvin, right? That's why we emit in the infrared by the same law as before. I should have a total energy density that is infinite. Well, that's not really the case. But more on that later, and we will continue to next week analyze more on blackbody radiation, and then also go to the transport of radiation. Thanks for today. The equilibrium case as a first example here, and started to discuss blackbody radiation, equilibrium radiation, introducing Planck's radiation law, spectral shape of it. With the sort of say caveat is that we actually just took it for granted for now, and that's what we'll do. We'll work with its properties today and analyzing that. Also coming to the basic definition of a quantity like the effective temperature, for example, which is very often used in astrophysical research, right? And we didn't really specify where it came from. And the reason for that, I mentioned already in the last class, is that we need a little bit more material in order to go there, but we will in the next chapter and see how actually, what the origin of Planck's radiation law really was. We will look at Planck's original derivation even in a sort of for now, we will just take it for granted. So we're going to continue with that exploration now of blackbody radiation. So last class, again, we discussed the various frequency-dependent properties. We looked at the Rayleigh-Jeans limit, the Wien's limit, the full spectral function, and also deriving then Wien's displacement law to actually get a connection how you can just look at the spectral, a spectra of, say, a star, and just by looking at it, get an immediate feeling for what the surface temperature of that star is, even though it doesn't radiate like a perfect black body. All of that we handled. Today, we're going to look at the, we can call it the integrated properties of the blackbody radiation law and what they can teach us, particularly about the various radiation quantities that we introduced in the previous chapter. Now, what do I actually mean by that? Well, I just mean that if you have a given temperature, then the integrated blackbody radiation law is just the Planck function at a given temperature integrated over all frequencies. Okay? Remember, there were no angular dependence in the Planck function. That will come back several times today. It's isotropic. Yeah? So, B nu of t, we know it had this dependence, right? Okay? So, this is actually left for you to do as an exercise. It's an algebraic exercise, not bad to do, okay? It is in the course book. The answer that comes out here is sigma T4 divided by pi, where sigma is the Stefan Boltzmann constant. And part, of course, of the task in the exercise is to see how this is just actually a combination of the fundamental constants that is part of Planck's radiation law. Okay? It is also, of course, given to you, its numerical value, etc., in the course book. The second thing we can just see here is that, okay, for B of t, the integrated properties is proportional to t to the cubed. Yeah? So the integrated value is higher the temperature becomes. So, all right, now let's connect this then now to some of the radiation quantities that we have introduced in the previous chapter. We start with the energy density. So the radiation energy density, we know, is just 1 over c integral over all angles, integral over all frequencies of the specific intensity, I nu, and then d nu d omega. But now we have said that the specific intensity is given by the Planck function, B nu, and B nu is angle independent. That is, it's isotropic. It doesn't contain anything there, right? So actually, we can just separate these integrals then and get this. I'm going to do an extra step here just for clarity, right? This is now as a function of t, of course, yeah? But, well, the first one we have done, that's 4 pi. So 4 pi divided by c. The second one we just gave down there. It's just this one. So this becomes just 4 sigma divided by c T4, which you often see as A T4, where A then, of course, is equal to 4 sigma divided by c, and it's typically called the radiation constant. That's just unfortunate because, you know, we have more letters to keep in our head, and A is not such an original letter. Anyway, but that's how it is. That is the radiation constant, and this is then the energy density for given temperature T of blackbody radiation. You can see, interestingly, it depends on temperature, but not on the material density, for example. Now, connected to this, I wanted to do a little detour before we move on to the other quantities that we have discussed. And that was that I will allude again to what we will come back to later in the course. And that was that, okay, what if now, instead of using the full black body radiation, we just use the Rayleigh-Jeans part, okay? That was the classical part I already said, right? Well, if you remember what we had then, this comes out. It was also isotropic. But this would be something, well, we can just do it here, right? We needed to Taylor expand this in the limit that h nu divided by kt was much, much smaller than 1, with the 1 Taylor expansion that we need to have in our head throughout this course. And then we saw that this becomes 2 nu squared. You get a k, you get a t, you get a c squared. H vanished, of course, Planck's constant. Yeah? And then the nu. But the thing is here that this contains nu squared. Yeah? So what happened to nu squared when you integrate from nu 0 to infinity? This goes to infinity independent of the temperature. And this was why it was called the ultraviolet catastrophe. It was already known that there need to be this some sort of cutoff that we discussed in the previous class at high frequencies, because otherwise the energy density of any given black body radiator would be infinite, which is of course absurd. So people knew there was something wrong. Right? That being said, this is a very useful law to use when this condition is fulfilled. Often, for example, in radio astronomy, which we will come back to. All right. That was the energy density of the black body radiation. Now we're going to look at flux. So, the flux, well, we know that black body radiation is angle independent, right? So, previously, remember we did the calculation that if we had this, I knew of theta and not of the second angle phi, then we already knew that if we put this in a Cartesian system, then we already show that x, fy equals to 0. But in general, the z component was not 0. Now we're going to see what happens when we plug in black body radiation in the z component. So we just use that again in its definition. I knew, which now is b nu, so we're just going to replace it by the Planck function. Yeah. Then you have a mu, the nu, the omega. Okay, where mu is the cosine of the angle, as we have seen for the c direction of the flux. This is also then what we typically call the flux, as discussed. So again, though, b nu is not a function of phi, no, but it's also not a function of theta. That is, it's not a function of mu equals cosine theta. So we can again take that, separate the integrals. Oh, holy moly. We get this out, and it was, what was it? It was sigma T4 divided by pi, right? And then we have a 2 pi from the phi part, and then we had mu minus 1 to 1, yeah? Mu, the mu, okay. But here we had this little nice integral. We have an uneven integral on an even interval, which is just 0 always. So indeed, we already sort of knew this, but the flux from a black body, isotropic radiation field, is 0. Indeed, when the radiation field is isotropic, we show that the flux, per definition, must be 0. You have everything, contributions, think about it as your rays of light, contributions from all different directions, so that the net effect in all directions cancel out. It is 0. All right. Now, we're going to look at the third interesting quantity that we have discussed. What was that? Right, that was the pressure tensor. And remember, again, if we make this approximation, it's only a function of theta first, okay? Then we already showed that it had the following form: 1/2 E minus P, 1/2 E minus P, P, where P now equals PCC, the radiation pressure, analogous to the flux. Okay, so let's evaluate. E, we have already evaluated. I took it away from the blackboard. Let's hope we remember it. PCC remains. Okay. We have Blackbody radiator. We have 2 cosines theta now, if you remember. So mu squared, yeah. The nu, the omega. So that's then, again, by analogy, this has no mu dependence in it either. There is a 1/c missing here. Yes, sir. 4 pi divided by c. No. Apologize. First, this one. We have the 1/c. I'm going to do this. Sigma T4 divided by pi. Yeah. 2 pi comes out from the pi integral, and then you have mu from -1 to 1, mu squared the mu. Now, this is no longer an uneven integral. It's an even moment of the radiation field. So this doesn't cancel anymore. Instead, if you evaluate this, it's just mu cubed divided by 3, right? So what comes out is 2/3. So you have 4 pi 3c sigma T4 divided by pi. Haha, but then we realize that this is actually just E divided by 3, which we sort of knew, since it's an isotropic radiation field, that 3 times the pressure, if we use that notation, has to be the energy density. So let's plug that into our tensor here. Well, then you see that indeed you get a diagonal tensor where the value is just the value of that. This is what we call the isotropic pressure, isotropic radiation pressure in this case. All right. So now we're going to use these properties that we have verified. The Blackbody radiator. I'm going to talk about some common definitions and astrophysical examples where this is useful. So we're going to start with like sort of a definition of what is called Teff, or the effective temperature. So in your Intro to Astronomy course, you might have seen a so-called Hertzsprung-Russell diagram, which goes something like this and something like this, with the intuitive leftward axis here. And if you put it not on a color magnitude, which is the observational equivalent, then you have something like the luminosity of the star there and the effective temperature of the star there. Yeah? And then, you know, you put your main sequence. Most stars live along there. The sun is around here somewhere. The hot massive stars that me and Frank works on are up there. Here are the supergiants. Here are the white dwarfs, and so forth. Right? But this is Teff on that. So what's that? Now, you might have heard definition of Teff is just the effective temperature. Is just the flux that the star emitted if it were a black body. But now you should immediately be a little bit suspicious, huh? Oh, but you just showed us 2 minutes ago that the flux from a black body was 0. So what's that all about? Well, the thing is that we have to, again, remind ourselves of something we did the first week, okay? You look at the surface of an object now. Here. I'm going to just sketch this. As a surface, okay? Now, of course, deep inside that body, you know, you might have radiation coming from almost all directions, such that if the radiation behaved like a black body, then the flux would be 0, right? Now, the definition of Teff, though, uses another thing, and that is that, okay, what if we now have emission only, well, say from a star in the upward direction from this surface, and that emission were as a black body, okay? So that means that you have something, and that could be what you calculate in your model, or it could be what you measure, yeah? That is then the, well, it's 2 pi, right? Because the phi integral has already gone away. And then it's mu minus 1 to 1. It's nu 0 to infinity, okay? Specific intensity, I nu. And then you have a mu d nu d mu. The other way around. Okay. So the whole idea here now is that, well, at the surface of the object, as we discussed last week, you actually don't have any incoming radiation. Imagine the plane here, and then stuff is only radiating in this direction, in the outward direction. There is no incoming radiation here because it's the surface of the object. Okay? So that means that all angles, if you put it in this format, that goes from there, and then all inward angles, they do not have any radiation. Right? So the only thing that contributes, if you want to calculate then the flux from in this direction, or the angles in the outward direction, given then by the theta angle there, yeah? So that mu equals to cos theta here again. And then, of course, in the general sense, you have to integrate over all the mu angles like this, yeah? We have already taken that 2 pi integral out, assuming that. But there is no incoming, which means that all angles from there to there is no contribution. So the radiation field then is not isotropic. It might have the same spectral shape as the black body, yeah, and that's what the definition of Teff is actually based on, but it's no longer isotropic. Okay? So you can, like we did, you can go back to the first week of classes and see when we did this in the generic context, right? Then the angles from -1 to 0, well, they all have intensity that is real 0, so they don't contribute to the integral. So the integral then is just 2 pi mu goes from 0 to 1, all frequencies, I nu, mu, d nu, d mu. Okay. And then we're going to leave a little wiggle room there, yeah, to discuss. But we're going to say, okay, what if we now say that the specific intensity is the Planck function? Well, then no longer we don't have the full integral here. We're only considering from 0, right? So it's not going to cancel anymore. So then Fc becomes 2 pi. This is then, again, the integral over the Planck function. Yeah? So that's sigma par divided by pi. And then we have that integral, which is just now mu from 0 to 1 over mu. So that's just 1/2. Okay? So what you can see happen now is that these cancel. This is just sigma T4. Okay? In the case of a black body. And that's where the definition of Teff actually comes from. So now we can say that, okay, in the generic case, we have some sort of specific intensity here, yeah, at the surface of the objects, and then we can assume that it's free streaming to us. So perhaps we measure it, yeah, or perhaps we measure the flux from the object, right, depending on if we can resolve it or not. And then we're doing that in some sort of frequency band, okay? And then we're using some sort of technique to estimate those that we do not observe. Alternatively, you can think about, okay, I'm going to compute a model on how the specific intensity interact with the material down here, and then how much is actually escaping the surface. And then I'm going to calculate that. And then typically that involves solving this radiative transfer equation that we introduced, and we will talk about much more during the rest of this week. And that's normally then gives a specific intensity, which might have an angle dependent, which it typically does, and it might be very frequency dependent. Might also deviate from the black body in the frequency dependent, in the frequency dependent quantity. Okay? And then we measure the flux from that. We calculate or measure the flux from that, and then a value comes out. Okay. And then perhaps we get out a very, a value like, I don't know, that is 10 to the minus 12. I'm just making a number up now, right? And that's like, okay, what does that mean? Well, it's very difficult. So a convenient way to then say this instead is that, okay, we're going to define this as sigma Teff 4, which then uses this relation which was derived for if it were a black body, emitting only the positive, yeah? But it's not necessarily that it has to be the black body. Okay, now, then we have that definition of the effective temperature. So, the correlation with the effective temperature and the actual then temperature of the object, of course, depends on how well can you approximate this emitting surface as a black body. And that can be very different for different situations, right? For example, if you now take a stellar atmosphere, so a star, okay, then the emission layers from the star are centered around what we call the photosphere. And we will discuss how we can define that in just a minute. But then, if you set up the most simplest model for such a stellar atmosphere that you can, which we will do later on in the chapter, then you will find that the effective temperature, or the flux temperature, of the star actually equals the temperature at an optical depth of 2/3. The optical depth we will formally introduce after the break today, but it's a measurement of how far into the object you can see, how transparent or opaque is the object. So for example, when I look outside today, I can see the building behind us. That means that the air between me to the building is kind of transparent. If it were a foggy day, perhaps I wouldn't be able to see it. Then you would only see the fog. Now, if that were the case, I could say that I am in optically thick conditions. I do not see the underlying source, which in this case is the building, because it is obscured. The light that is gathered from that building to my eyes is obscured by the intervening material, which is optically thick. Today, the material in between me and the house is very optically thin, transparent. The optical depth is not very high. I can see it, okay? And the transition between being optically thin and optically thick is on the order of 2/3 or 1. Really, it's more of a function because some photons will escape from optical depths of 2/3, some from 1, some from 2, etc., etc. On average, it's on the order of unity. And this is then why, in a star, for example, the effective temperature is related to the actual surface temperature of the star, because from these layers, the light is emitted, is vanishing to outer space, and we're seeing those. Okay? Again, this now is also a way to define what we call the surface of the star. It's a gaseous object, so it doesn't really have a solid surface like here, right? So we have to define it in somewhere. And often this is defined at the layer where the optical depth is 2/3. But this also means that it's different for different wavelengths. We haven't come to this, but the optical depth involves a wavelength dependence. I didn't do that here, or frequency dependence. And this means, for example, that in the optical light, visible light here, the star looks a certain size. We define the photosphere of it to be on the order of tau 2/3 in the optical. But if we look in the radio wavelength, then the size is different, because the optical depth is different there. And we'll come back to that. Okay? So that's a first connection there. Now, a second situation, there are many situations. I will just take a few. Is if you have like an accretion disk around, say, a supermassive black hole, yeah? Then under certain circumstances, this could be approximated, and this is something that you will do more with me if you are in the master's program after Christmas when we do galaxies and cosmology. Yeah? We're gonna, continue this picture. We have the central mass here. We have the accretion disk now around, just here. And then we're going to make the assumption now that this disk, so you have to think about it in the plane here, yeah, is geometrically thin. That means that the delta C, if you think about C this, is very, very small, that it can be neglected. That's what I mean with a geometrically thin disk. But it's optically thick. And that means that if you take this geometrically thin disk like this, and you shine something on top of it, it doesn't get through. It's optically thick. So a table would be geometrically thin, but optically thick. If I look here, I can't see what's beneath. Simultaneously, if somebody's under the table, looking from there, looking up, can't say. It's geometrically thin, but it's optically thick. Now, that has the important that if we look at our little delta r here now, a little delta r, yeah, from this little ring here, it will emit there, and it will emit down, okay? And since we have assumed these assumptions, we can say that, well, if it's optically thick and idealized, then it emits like a black body, okay? So, if it emits like a black body, then your delta L will be your flux times your delta A, where delta A is the radius. Yeah? Now, the flux from a black body, that's good. We can do that by our radiative processes notes. We know that this is sigma T4, that you need to look up if you have forgotten it. Delta A from this is sigma T4. Now, the total area here is, well, you have the circumference of the disk, 2 pi r, this we know, I hope, times delta r, which is the thickness here. So then you get the total area of a little annulus. However, here you have to multiply this by a factor of 2, because the disk can, of course, emit up, but also down. So the total surface area is the disk up and the disk down. Again, you can make an analogy what we did in radiative processes courses and a lot of other courses, where you just, okay, but the luminosity is just 4 pi r squared sigma Teff 4. Where does that actually come from? Well, that only applies for a spherical object, like a star. Because 4 pi r squared is the surface area of the star, the total surface area of the star, like here. The flux is what the flux is, but we associated the effective temperature, sigma Teff, with the actual flux. If this were a black body, it would be sigma T4. We went through all of this, but now we just have to consider a different geometry. That was just 2 examples of how we can use these ideas to connect them to various astrophysical objects. And actually, the idea of a photosphere we can extend at an optical depth of 2/3, we can extend even further. We can even talk about, and we shall, about the photosphere of the universe. And that you might have heard about in your Intro to Astronomy course again, called then the era of recombination. Okay, now what actually happens during the era of recombination is something that we will study in some detail, at least, in one key application of the course, 8.1, that we will do later. Yeah? But the thing is that during that era, the optical depth, when we go from today and back in the path, increases drastically, such that you hit essentially an opaque wall. The universe becomes opaque, it becomes optically thick, and that's where the cosmic background radiation photons are emitted that we can see today. Typically, you also refer to this in this context as the surface of last scattering, which again should probably be, like I referred to in the beginning, some sort of, it's more of a cloud, because it's not like it's a complete surface like that. Some photons will emit a little bit higher optical depth, some a little bit lower, okay? And we will come back to that again. And also now, I've talked a lot about optical depth, but I haven't actually said what is this optical depth, and that's something we will do after the break, where we discuss some simple examples of the radiative transfer equation now. Okay.